the Father of Waters across the river from St. Louis lie the mills of the Granite City Steel Company. This community did not derive its name from the presence of granite quarries in the vicinity, but rather from the granite-ware kitchen utensils manufactured here. This ware was so called because of its enamel coating, which originally contained finely pulverized granite rock, producing a finish as smooth as highly polished stone. This now famous product was first manufactured in the 1880s by William F. Niedringhaus, who owned and operated the St. Louis Stamping Company in partnership with one of his brothers. Mr. Niedringhaus chanced upon this formula during a trip to Europe, where in a tiny village he discovered a small factory producing such enamelware. Realizing the great future for this product, he acquired the method and patent rights for manufacture, which he brought back with him. Thus, he founded one of the nation's major industries and gave its product the name which it still bears, Granite-ware. The company expanded, and in 1878 decided to build its own steel plant. 2,700 acres were purchased on the Illinois side of the river to provide for the new mills and the town which was inevitably to grow around it. Thus, what was nothing more than marsh and scattered farmland in 1893 is today a town of 26,000 people, the center of an active industrial community. Our story begins in the raw materials yard, where pig iron, iron ore, manganese, spiegelisen, and scrap iron are stored. These materials, such as this steel-girdered scrap, are loaded by magnets into buggies or charging boxes. Pig iron, which constitutes a major item in the making of steel, is also loaded into these boxes for conveyance to the furnaces. With 10 such furnaces, each capable of producing 60 tons of steel every 8 to 10 hours, about 50 freight car loads of raw material a day are needed to keep them going. This enormous consumption keeps these little dinky engines hustling to satisfy the voracious appetites of these furnaces as they push their loads up the inclined railway to the charging floor of the open hearth furnaces. Upon arrival, the material is promptly charged into one of the furnaces by this special charging machine, which picks up a box, thrusts it into the flaming maw, turns it upside down to empty the contents, and then draws the box out again. This is continued until the full 75 tons of material are fed into the furnace. The open hearth furnace is carefully maintained during the 8 hours it takes to melt the mass. And speaking of melting, try to imagine the intensity of this ferocious heat. You probably can't. But here's what 3,000 degrees of roaring inferno looks like. That metal is dripping away like a lump of ice in the summer sunshine. When the pig iron and scrap have become liquid, special attention is given to the slag which forms on top. And at times, fluorspar is added to make it more fluid. And now, when the mass has reached a completely liquid state, the melting foreman reaches into the furnace with a long spoon to take a sample for analysis. This sample is poured into a small mold to solidify. This is a little like dipping out a sample of fudge to see if your candy has cooked properly. But this procedure is considerably more scientific and hotter. You can't pick up this sample with your fingers. When the metal is cooled to a solid state, though still quite hot, it is knocked from the mold to be taken to the chemical laboratory for preliminary testing. Here it is placed in a drill press, where a hole is bored in the still warm sample block, to obtain the fine drillings necessary for the chemical analysis, which will determine the impurities still present in the steel. These scientific sentinels are on duty constantly, making quick tests for the presence of phosphorus, manganese, sulfur, and other elements which are important in steel production. No time is lost in transmitting the laboratory report back to the open hearth men, which is done immediately over a telautograph system. After reading the chemist's report, the melter makes the necessary additions to the steel to bring it up to proper requirements. For high carbon grades of steel, other samples are poured every few minutes, precious time being saved in making the carbon determination by subjecting the sample to examination by a clever electromagnetic instrument known as a carb analyzer. This gives an immediate report as compared to the 10 or 12 minutes required for a chemical analysis. As the molten steel becomes purified, the huge ladle is moved into position on the pit side of the furnace to receive the torrent of fiery liquid when the heat is tapped. Everything is made ready for the big moment. The tap hole is carefully dug out and the connecting trough cleared of all obstruction. Only a small dam of refractory material now remains as a plug to hold back the furious mass of surging steel, lashing and raging inside the furnace. A crew of men on the front side of the furnace are working with a long bleeder rod to knock out this final obstruction and release this roaring inferno. Of incandescent liquid fury cascades into the huge ladle. The men must work quickly now, shoveling in the various necessary ladle additions, such as ferrophosphorus, ferromanganese, ferrosilicon, which may be required to give the steel the desired chemical properties. The exact amount of each addition has been carefully calculated from the previous laboratory analysis. As the ladle fills, the slag containing impurities rises to the surface and is allowed to overflow into the pit below. Then, when all of the steel proper is out of the furnace, the ladle is conveyed to the ingot mold. The huge crane starts off with its incredible load of over 100 tons of combined steel and ladle. Slowly and cautiously, this fiery cargo is backed and lifted. Each motion must be made with careful and alert consideration of safety. For although no one stands within range of the splashing slag, the ladle contains a terrific inferno of potential destruction. And it is to the credit of the steel industry that an excellent safety record is maintained with conditions such as this a matter of routine operation. At its destination, a valve is opened in the bottom of the ladle, and the molten steel is allowed to run directly into the ingot molds below. The operator has complete control of the flow of steel through a lever attached to the valve rod, extending through the liquid metal itself. Care is taken to pour or team the steel at the proper temperature, and this is rigidly checked by an optical pyrometer. This particular grade of steel still shows considerable agitation due to escaping gases as it slowly solidifies from the outside of the mold to the center. Additional samples of steel are taken at the time of teaming in line with the company's policy of keeping a constant check on its product. Finally, the empty ladle is carried away, and we come to a brief lull in operations while waiting for the poured steel to cool. Usually, a period of about an hour and a half is allowed for the steel to solidify in the molds, which are then moved into another position for what is known as the stripping process. Here, another crane of special design grasps the ears of the mold, and while the plunger in the center holds the ingot down, the mold is lifted, just as easy as it looks. However, this newly cast steel is still radiating a temperature of 1,500 degrees. The ingots rosy with a healthy glow, are weighed. And the open hearth department, conscious of a job well done, bids them farewell and goes about its task of preparing another heat. In the meantime, the present ingots are trundled along to the soaking pits, which is aptly descriptive of what happens as they are transferred by crane to oven-like vaults, where they are literally soaked in a temperature of 2,250 degrees for a period of 6 hours. This is done to bring the ingots to a uniform required heat for subsequent rolling. The crane operator deposits the 12,000-pound ingots in the pit carefully and deftly. This pit is heated with natural gas, and after all of the ingots are in place, a steel cover slides over the top to seal the opening. Careful control is exercised over the heating carried on here in the soaking pits to prevent damage to the steel, and also to make sure that the ingots are brought to proper rolling temperature. The ingots have now been heated thoroughly and uniformly, and are ready to be conveyed to the slabbing mill by this operator, who manipulates the crane from a cab well insulated from the terrific heat radiated by his glowing cargo. Here we are about to see how a steel ingot is rolled into a slab. Of the ingot square and straight, it is now passed through this set of vertical rolls called an edging mill, a treatment which each slab receives several times. As it makes its final pass through this mill, the roller checks the width of the ingot with a measuring rod. The thickness, of course, is determined by the setting of the rolls. And now, having reached the desired width and thickness, our ingot has officially attained the status of a slab. Accordingly, it passes along to a slab shear that chops off the ends and cuts the metal to a specified length. It looks very simple here, like cutting cheese. But even though the slab is sheared hot, it takes a lifting power of 1,000 tons to cut through it, a figure equal to the combined weight of over 13,000 men. This completes the first rolling operation, and the cut slabs are now carried by conveyor into the slab yard, where they are automatically stacked as they leave the exit end of the conveyor. At proper intervals, a waiting crane removes each pile of slabs and sets them aside to cool. Inspection at this point is important, as all surface defects must be removed before the slab is again rolled after heating in the slab furnace. As one slab is pushed into the back of the furnace here, it forces another out the front, creating a continuous cycle operation. It requires about 2 hours for the slabs to pass through the furnace, wherein they reach a temperature of 2,250 degrees. The heating of these slabs is supervised at several points on the side of the furnace through small doors, which enable the operator to determine the uniformity of the heat. Here you can see the actual movement of the slabs as the insertion of a new one forces the entire row down the line. And here comes a slab out of the exit end of the furnace, ready for its journey through the roughing mill or scale breaker. The slab is 4 inches thick at this point, and this mill breaks the heavy scale accumulated in the furnace, while a powerful spray of water washes it from the slab. The slab now enters the 3-high roll roughing, a mill which works the steel forward and back, making it longer and thinner with each rolling, until it is reduced to proper size for the strip mill. A pair of edging rolls on this mill prevents distortion of the slab by keeping the sides straight and smooth. As the long strip of steel leaves the roughing mill, it passes under a radiation pyrometer, which records the temperature. Usually, the steel is held here for a few seconds to allow it to cool to a suitable degree for final rolling. Once again, the steel is fed through a scale breaker and hydraulic spray to clean off the oxide which is formed during rolling in the roughing mill. And now the strip is off for its long ride through the 5-stand continuous finishing mill. These gigantic strip mills have revolutionized the steel industry by increasing production with less physical effort. They have improved the quality of the product so much that hundreds of articles are now made from steel, whereas a decade ago it would have been impossible to utilize this material for such items. To the untrained eye, everything rolled on this mill would seem much the same, but actually it is divided into 3 classes: wide plates, heavy sheets, and coils. You'll see a great deal of the coils later, as they undergo a spectacular workout. These wide pieces are plates, which are used by the heavy steel fabricators, and they are transferred to an adjacent building for necessary finishing operations. Here, after being leveled and cooled, the plates are rolled over to a gigantic shear, where they are cut to proper size. While the shearing takes place, the plates are given a careful inspection for surface defects and marked with proper identification numbers in readiness for shipping. This plate will very likely find its destiny as part of a boat, a bridge, an oil tank, or a skyscraper, or perhaps even as part of a freight car, such as the one into which it is now being loaded. These plates have a wide variety of uses in our modern progressive civilization, and they literally form the backbone of construction. Back at the mill again, we see how heavy sheets are made. The process is the same, except for speedier rolling and greater reduction. These mills consist of 5 stands of 4 high mills, each revolving faster than the preceding one, to take up the slack of increased elongation. The strip races down the run-out table, still hot and glowing, on its way to a flying shear, one of the busiest and noisiest machines in the plant. This flying shear cuts the long strip into uniform lengths quickly and efficiently. After they are cut, they are piled quickly and automatically to allow for annealing while still extremely hot. After sufficient cooling, these sheets are put through a so-styled temper pass, or light coal rolling operation, where they are flattened in a heavy roller leveler. Then a continuous shearing line trims the edges to ordered dimensions, and after one more leveling, to ensure proper flatness, the company's trademark is stenciled on. Instead of tin plating, some of the heavier sheets receive a galvanized coating of zinc, requiring pickling for oxide removal. The prerequisite of all plating is a clean, fresh surface which will receive and hold the coating material without creating surface flaws or peeling. To ensure this, these sheets are fed through a rinse of hydrochloric acid, immediately preparatory to their actual galvanizing. After passing through this acid bath, they move through a series of rolls which guide the sheets downward into the galvanizing pot, where they are immersed in a bath of molten zinc. In some respects, the galvanizing process is more spectacular than the tinning operation, especially in end result. As the sheet emerges from the exit rolls, the zinc coating crystallizes, and the bright spangles indicative of galvanized steel begin to appear on the surface, sparkling like thousands of tiny stars. Many of these sheets are scheduled for corrugation, but they are marked by stencil before this process. The actual corrugation is done in this machine, where the sheets are fed through a pattern roller, which makes them ready for use as corrugated roofing, side sheets, culvert pipes, and a score of other varied destinies. Back again at the mills, we are about to see the making of coiled hot rolled strip. At each mill stands an alert operator who controls the thickness of the steel, while the speed of all mills is synchronized by one man on a high control platform, where he has an unobstructed view of all mills. The production of this type of strip calls for an even greater speed than the other produced, and it emerges from the last stand of the mill at a rate of 1,400 feet per minute. Because of its great length, around 850 feet, it often loops up on the roller table before the front end shoots up an incline, where the coiling machine subdues it into a tight, compact coil. These coils are conveyed automatically from the machine to be marked and weighed, and then sent to another department for further processing. And now we follow the coil to another part of the plant, where a great deal of attention is in store for it. You saw it rolled and reduced hot, but it is to be reduced still more to a much lighter gauge on what are termed cold reduction mills. Before that, however, the steel requires special preparation, and here we see how it is readied for that process. The coil, having been tightly wound while hot, now requires unwinding, or more properly, loose winding. To achieve this, the sheet is fed through a machine known as a loose coiler, which separates each ring of the coil so that it can be acted upon by an acid pickling bath. This pickling process removes the oxide formed in hot rolling, and as it rotates in the vat of hot sulfuric acid, the solution reaches all surfaces. All trace of dark oxide accumulation is removed in this operation, and it will not be allowed to reform. The coil then passes to a swiftly agitated cold water bath, which washes off the acid. Finally, in a third bath, it receives a light coating of oil to prevent it from rusting. The pickled coils weigh about 2,500 pounds, and in the interest of production efficiency, 3 of these coils are usually welded together for the cold reducing process. Accordingly, to prepare for this process, the loose coil is now fed through a tight winder, which wraps it neatly and compactly upon a heavy reel. After the first coil is in place, a second one is put through the machine until it meets the end of the first coil. Then the 2 ends are carefully aligned and joined by an automatic gas welder, which moves across the 2 pieces of steel, creating a perfect union in a brief matter of seconds. The third coil is joined and wound in the same manner, and a gigantic crane moves into position, lowering a hook to hoist the assembled 7,500-pound roll aloft and start it scooting to its destination. These coal-reducing mills are 2 in number, and the housings are similar in size and shape to the 4 high hot mills which we saw previously, but these are of a single stand. They also contain 4 rolls for strength, just as the hot mills. The end of the coil is fed slowly between the 2 work rolls and fastened to a reel on the other side of the mill. An enormous pressure of 3 million pounds is put on the rolls, and the reducing process begins. A flying micrometer is placed on the edge of the strip with an indicating instrument at the operator's elbow, which tells him how close he is to adhering to the proper thickness. The mill is reversible, and the strip passes back and forth several times. When the coil has reached its proper gauge, it is taken to a cleaner line to remove the lubricating oil from its surface. And incidentally, that surface would extend over 2 miles if it were unwound. After cleaning, it is coiled once more for annealing. The steel is very brittle and stiff at this point due to rolling, and the heat of annealing will make it soft and malleable so that it may be worked without breaking. The coils are placed on this furnace bed, one on top of another, where a box-like cover is to be lowered over them. This is merely an inner or protecting cover, and the bottom will be carefully sealed with sand. The unit which actually does the work is a large outer cover known as the radiant tube annealer. After it is in place, it is connected with a line of natural gas, and heat is radiated through a system of tubes on the inside. Delicate control instruments regulate a constant temperature for a given number of hours for uniform annealing. And now, about a week later, after the coils have again cooled to room temperature, they proceed to the next operation called temper rolling. This operation is done on a mill similar to the coal reducing type, but the steel goes through under much lighter pressure. Here the steel, dead soft from annealing, acquires proper temper, and this process also furnishes the kind of surface the customer requires, from a high gloss to a dull finish, in keeping with particular requirements. This is the last of the rolling operations, and we'll all have to admit that the coil has really been through the mill. But it's tough enough to take it. And it has to be tough, because there are still a lot of things in store for it. As soon as it finishes its stint through the temper mill, another inevitable waiting crane lowers into the scene to receive the coil as it slides off the mandrel where it has been tightly wound. This specially balanced hook is guided through the hub of the coil to be swung aloft on another journey. Now, after all the coiling, rolling, and recoiling, look what happens to the steel here. It gets cut into small sheets of specific length and width according to customer orders. Let's go back and analyze the working of this clever machine in close-up form for a moment. This particular cutting unit, known as a slitter, first trims the edges to the proper width by means of an efficient set of circular shears or sharp-edged overlapping wheels. In the meantime, a micrometer is registering the thickness of the sheets. This instrument is similar to the one used on the coal reduction mills, and its function is to detect off-gauge spots in the coil. When it records the presence of improper thickness, the offending sheet is automatically kicked off to one side. This flying shear is a clever machine which moves along at the exact speed of the steel as it makes a cut. Watch the action in slow motion and see how precisely and efficiently it does the job. That's a nice gadget to keep your fingers away from, unless you like your manicures close. And now all of the sheets which have passed the inspection of the flying micrometer proceed to the piler, where an electric eye counts and records them. This finished steel will go into metal furniture, cabinets, automobile bodies, frying pans, cooking utensils, and numerous other products which call for this bright, shiny material. Those sheets destined for tin plate first undergo a pickling operation to remove any vestige of oxide from the surface. After the sheets are loaded into one of the 3 racks of the pickling machine, they are swung around for a dousing in an acid bath. At the same time, another rack of sheets just out of the acid swings into position over the wash water, where it is lowered for a thorough rinsing. Meanwhile, the 3rd rack is being unloaded by the operators. This pickling process is quite similar to that which the steel received in coil form, except that at this point the sheets are packed into water-filled containers to protect them from the oxidizing action of the air during transportation to one of the tinning machines. The formidable load is whisked aloft by another crane which conveys the sheets, tank and all, to the long line of tinning machines. Here, with the dexterity of long experience, the crane man gently deposits them beside the waiting operator. This man takes about 50 sheets at a time from the tank of water and carries them to the entry side of the tinning machine where they are inserted. A magnet arrangement picks up each individual sheet and puts it through a series of rolls and down into a bath of molten tin. The pigs of pure tin are charged into the machine from the side and gradually melt down into the bubbling solution. The sheets remain in the molten mass only a few seconds. As they emerge, they pass through a finishing bath of palm oil, which floats on the surface of the molten tin. Here they fairly radiate their new personality as they drop down onto this conveyor, which carries them to the cleaner line where the excess palm oil is removed before the final polishing. Bran middlings are used to absorb this oil, and then a series of soft cloth rolls brush off the bran and polish the surface. This type of material is a high-quality product, one of the most expensive production items of the plant. Cleanliness is a prime requisite, and even the polishing rolls themselves are frequently vacuum cleaned. As the gleaming silver-like sheets leave the machine, the supervisor periodically examines some to check consistency. In the assorting room, the tin plate is carefully inspected and graded. Tin plate used for food containers must be of the best and entirely free from flaws. After inspection, the plate is counted and put up in packages of 112 sheets each. These units are carefully wrapped to prevent any possibility of damage in shipment or storage. The next time you open a can of tomatoes or beer, you should have a greater respect for the humble tin can, the material for which required so much work and care to produce. Certainly no product was ever polished and groomed more carefully for presentation to a waiting world than a sheet of tin plate. And now, ready for use, the sheets are loaded into boxcars. This car looks comparatively empty, but actually it is filled capacity, for these few packages weigh the incredible amount of 100,000 pounds. Thus does Granite City maintain tradition and contribute to the progress and industry of the country. Its products find their way into everything from barges to freight cars. It also goes into trucks of all kinds. Indeed, transportation is vitally dependent upon steel. It goes into the very road signs which safeguard that transportation and into the bridges which carry the nation's traffic. In the far-flung agricultural regions, Granite City steel serves the farmers in tractors and other implements of cultivation, as well as providing corrugated sheets for barns, buildings, and culvert pipes. And after the food products are harvested, they are preserved in cans fashioned from tin plate. Millions of cans of fruit, vegetables, meat, beer, and other items, protected thus until they are ready to be served. And here again, in cooking, steel renders another service in the form of granite ware and kitchen utensils. Even the tanks which provide us with water are fashioned from steel, as well as the massive fuel containers and boilers which serve our daily needs. Thus, in an endless cycle of service, with its products reaching into countless everyday necessities and conveniences, the Granite City Steel Company maintains tradition with over 60 years of contribution to the unending progress and comfort of mankind.